You have to have lower pressure in the bottom to draw air through those heads, and if you increase the pressure in the bottom, you'll slow down the rate that air goes through the heads. Now this cabin heat, carb heat muff, the way Mark's got them located is fine. You can put them on in any way that you want, really. There's been some postings on the Jabiru engines list lately about, do you put the probe right against the head, or do you take the compression washer off the plug, put the probe on, and then put the washer back on the plug? Jabiru has told us that they prefer the method, take the washer off the plug, put the probe back on the plug, put the washer back on. And again, this is a question I don't get too much anymore. I think we're into getting our customers a little more educated in the way of doing things. Those probes are pretty soft, and if they're right against the head and things don't go exactly right, they will deform just a little bit when you torque the plug down, and then they'll have a tiny exhaust gas or combustion gas leak there. And it used to be I got a call once or twice a month saying, help, I got one cylinder that's running the cylinder head temperatures of 550 degrees. I knew exactly what was going wrong there. He had a little bit of a leak, and it was getting that probe nice and hot. And the probe was reporting the temperature right there where the leak was coming out of the hot combustion gases, not reporting the temperature of the head itself. But it seems like
washer probe.
Yeah, take the washer off the plug, put the probe on, put that washer back on. Seems like the washer with that sort of convex edge on the head side, that seals pretty good in there. And then it's not nearly, you can still get a leak if you've got that probe distorted. And again, it's tough to get the probes in there. You can't put your plug socket all the way down the plug and still have room for the probe there. You put your plug socket on just barely enough to engage the hex nut on the plug, because we try to push on and there just isn't room. But very rare do we have a problem with leakage and a probe reporting a very high temperature if you put them on that way. Now the other thing that happens, Jabiru says head temperatures are to be within a certain range. And if the probe is right on the head, the probe will be reporting roughly 25 to 40 degrees more temperature than it will report if it's between the washer and the plug. So, if you're seeing 360 degree temperatures with the probe right on the head, in actuality you probably have about 330. So it will report higher head temperatures than, it reports the accurate head temperature from the location it's at, but that's not the location Jabiru measures it. So that's This talk I often call unlocking some of the mysteries of the Bing carburetor. This is a little bit more complicated than a typical carburetor because it does automatically adjust the mixture for you as you gain altitude and descend, and it keeps your mixture going into that Jabiru engine at a fairly constant, keeps it where it should be. Now, a lot of people have said, well, it's really not effective above a certain altitude. Well, I'll give you an example. The Israelis are using this Bing carburetor on a Jabiru 2200 engine on an unmanned aeronautical vehicle, a UAV. I guess they keep track of some of their neighbors there. Up to 24,000 feet in the stock configuration. Okay, so it does work. It does work. I've personally been up to 16,500 feet in a Jabiru airplane with this on it. I think I lost about 50 degrees of EGTs by the time I got up to 16.5, but the Engine still ran well. I had lots of power. No problems at all. So that's it does work. I guess my objective today is to give you a close understanding of what this carb is made of and how it works, because it will be important for each of you to make sure that it is tuned, and that's the word we use, tuned to your propeller and airframe configuration. What controls the mixture on this actually is the combination of prop loading and airframe drag. That, in conjunction with the size of the jets in the carburetor, controls the amount of fuel that it lets into your mixture. So everybody's airframe is a little bit different. You know, some Zenith 601s are built real clean and they got wheel pants and are slicked up just a little bit. Look at Tony's out there, he's got those big wheels and so forth. There's no attempt to make that one a real slick airplane. Downstairs we have our Lightning airplane that on the same engine will fly 175, 180 miles an hour in cruise. We also have a Zenith 701 downstairs that you've seen us work on, and that's going to be 70 or 80 miles an hour in cruise. So airframe drag, prop loading, so forth, is a little bit different on every airplane, every home-built airplane, unless you have a couple of builders who happen to build them exactly the same, and that's rare. So I want to start by taking this Bing carburetor apart and showing you the parts that are inside it as I take it apart. Mark, would you hand me that jet wrench that's right in there? Okay, the fuel bowl is already off this carburetor. And inside the fuel bowl, let me back up just a minute here to the inlet in this carburetor. Bringing fuel in comes in right here in this nipple. Fuel then goes into the fuel bowl, and as the fuel bowl fills up, the floats here rise up, and there's a valve in there and it shuts the fuel flow off. So let's begin by taking these floats off. There's a pin here that normally it's a friction fit driven in, but I have it loose in here. Pull this pin out, and then the floats will come off in your hand. There's the pin. Here's the floats. There are some carbs that Bing makes that do not have the alcohol resistant floats in them. Make sure if you're ever planning on using autogas that you make sure they have alcohol resistant floats. In the float bowl chamber then is a little orifice here. That's where the fuel actually comes in. Fuel comes in from your tanks into this nipple, winds up coming in through this little orifice right here, the bottom one as we look at it. Fuel flow is controlled when the bowl gets full by a little valve body. This valve body is attached to the floats with just a little hairpin spring that slides onto this tab right here. Okay, and this tab is what actually pushes this valve. The valve sits in here like so, and when the bowl gets full, the floats come up, pushes this valve in, closes the orifice inside of the jet here. There is a little bit of cushioning to this, and that there's a little spring on this valve body part, and I'll pass this around. You can see that there's a little spring there, so the more gas that gets in the bowl, the harder it pushes on this, and eventually we'll shut it off. So I'll pass that around. When it gets around, just make sure it comes on back here. Okay, that takes care of how the bowl is filled. The next part I'll talk about is the jets themselves. There is a column of jets in this carburetor, a main jet and a needle jet. Now the main jet is the ultimate limiting factor in how much fuel is going to go into your engine. because everything has to go through the main jet. So that's the ultimate limiting factor. When your engine is under wide open throttle, then all the restrictions will be removed out of the jet column and the main jet will be controlling your mixture. Now I'll show you how everything else is controlled in a minute, but keep in mind that if your aircraft, when you give it full throttle to climb out or full throttle, straight and level, whatever, if your engine doesn't run right at full throttle because of a mixture problem, main jet is the culprit at that point. Not needle jet, not idle jet, it's main jet.
Because he's the only one in play at that.
Yes, that's the only one in play at that point.
At full throttle.
At full throttle. Now I'll take my handy dandy jet wrench here. That's what I was afraid of. Normally the main jet, do you have your little wrench there still? Out of sight. The main jet is screwed into this brass spacer is what they call it. So we'll hold the spacer and turn the main jet, and there we come out. The main jet has a little washer above it, but this is a Bing main jet right here. These are available in a wide range of sizes. From Bing Agency International in Belvedere, Kansas, is the Bing distributor for North America and South America, I believe. They have every conceivable jet that Bing has in stock there. About $6 for a main jet. I'll pass that around, take a look at it. Now in the jet column, as the carburetor would be like this, above the main jet is what's called a spacer. And the spacer threads into the carburetor body itself. We'll remove that out. And there we are. That's nothing more than a brass fitting that separates the main jet from the needle jet itself. Simple little part, does nothing other than space the two jets apart. Pass that one around. Now once that spacer is out, the needle jet, or sometimes people call it the mid-range jet, will fall right out. You see I'm holding the carburetor upside down. Hold it this way, there I have a needle jet. Needle jets, there is a tapered needle inside this carburetor that's controlled. It's attached to a diaphragm and changes in vacuum from the engine and the changes in ambient air pressure of the intake air moves that diaphragm up and down, moves that tapered needle up and down inside this diaphragm, and changes the amount of fuel that can come into the engine. So that's the actual jet that controls mixture in settings from, let's say, 3/4 throttle down to 1/4 throttle, the mid-range of RPMs. The official term is needle jet, but like I said, some people call it the mid-range jet. I'll pass that one around. Now, as I said, inside here is a needle, and that needle is attached to a diaphragm. So to get to the diaphragm, we'll remove these two screws in the dome of the carburetor. And if this was an operating carburetor, you'd see a little spring in here that pulls the choke back to the closed position. You have to take that off the dome before you can get it apart. But once that is these screws are out, and we can take the dome off of the carburetor, and there's just effectively all it is a dome. There is a spring in there to assist pushing against engine vacuum, and then the needle itself is attached to the diaphragm along with this piston in there. Now let me back up a little bit. The final piece at the top of the jet column is called, anybody know? Nope.
The speed jet.
Nope. This is called an aerator. Okay, that's all it is. Let me show you how this all stacks up. You have the main jet at the bottom of the jet column. On top of the main jet is the idle jet, or not the idle jet, the mid-range or needle jet. And on top of the needle jet is the aerator, which sits in there like that. So as fuel is being drawn into the carburetor, and what draws the fuel into the carburetor? Bernoulli's principle, Venturi effect, whatever you want to call it. It also draws a little air from on top of the bowl, the fuel level of the bowl, and helps atomize that fuel, or aerate the fuel. That's why they call it an aerator. So that's your jet column. And then the tapered needle slides down into that, and as prop load, engine vacuum, or outside air pressure changes, this needle goes up and down and changes the amount of fuel that can escape through these jets. Okay, any questions on jet column and how this all physically or mechanically comes together? Okay, let me just cover a few additional things in here. There is one more jet in this carburetor, idle jet, and then there's an idle air screw. No, I don't think that'll make any difference either, because it's up here. Yep, we aren't down there. The idle jet idle jet is the one that meters the fuel in when you're at 1100 RPM or below. Idle jet is sometimes a little bit finicky in that it's a complicated jet. The most expensive jet, it costs about $17. And it's not just one hole in it like a main jet, but you see there are a number of small little holes all around this. And it's not a frequent occurrence, but it does happen that some debris will get past your fuel filter, or there'll be some sludge or something, and it will clog up these little holes in the idle jet, and it is just about impossible to get that thing clean once it gets plugged up. I've had a couple of them from time to time that have plugged up, and we've blown air through them, run safety wire through them, cleaned out, put them back in, and they just still don't work. Put a new jet in, it works fine. So I'll pass that around as you're, so if you come up with some idle problems that you can't fix with the idle air adjustment or the idle mixture adjustment screw, then most likely a new idle jet would be in order. Working in conjunction with the idle jet is the idle mixture screw. Now there's again a passage inside this carburetor where fuel flows through to the idle jet, and here's this screw right here. This is outside of the fuel bowl. This is the only adjustment outside of the fuel bowl that controls the amount of fuel that can go through that little passageway and into the idle jet. So as you set this to achieve a smooth idle, the typical Jabiru installation, you screw it all the way in so that it gently bottoms out, screw it out about a turn and a quarter, and start there. In really cold weather, you might need to richen your idle mixture to get a better idle. So to do that, you would turn this screw out, or counterclockwise, turn it out another quarter turn, half a turn. Now, Any of you guys flown Rotax two-strokes? This is opposite of the Bing 54 carburetor with a two-stroke. That limits the air, this limits the fuel. So turning this one in will lean it out. The Bing 54 carburetor on a two-stroke, turning it in limits the air and richens it up. It's exactly opposite. But all this is just a little needle that shuts off fuel in a passageway. We'll get that out of here too. Okay, all that is just a little needle valve. Farther,
Bigger version of the diaphragm cover
yeah,
on the motorcycle.
yep. Other mechanical features in the carburetor bowl itself. Here we have a choke arm. You would hook your choke cable to this. Choke would be off there, and pull here for full choke. You have a throttle arm here. This throttle arm fitting is not Bing, this is a Jabiru fitting. And this fitting limits the opening of the butterfly to 75 degrees. According to Bing, max flow through the carburetor occurs at 75 degrees. If you go to 90 degrees, it decreases flow through the carburetor, and it exposes the rod that the butterfly is on to the airflow, creates a little turbulence in there. And go back to a little storytelling now. The first 300 or 400 Jabirus did not have any limiter there because Bing had not provided the information to Jabiru, and that butterfly could open 90 degrees. The first engine that I had on my Titan, when you gave it full throttle climbing out, you'd lose about 150 RPMs over what you'd get if you just pulled that throttle back just a little bit. And we never understood why. We thought it was our air filter or mixture or jets or something else. And finally, Bing's a tough company to get information from. They shared with Jabiru that max flow is at 75 degrees. So Jabiru designed this little throttle arm with a limiter right there that takes that butterfly to 75 degrees and no more. So that's not a Bing part, that's a Jabiru part. A very important little fitting on the carburetor right here at the top, as it would be on your engine, would be on the left side of the right side of the airplane, above the fuel inlet. This little nipple here is a carburetor bowl vent. Now again, this is a factor in the altitude compensation on this carburetor, in that the amount of air pressure in the fuel bowl determines a little bit how fast that fuel is pushed through the vent. You put a little more pressure in your bowl, the fuel goes through the jet faster and will actually richen the mixture up. A little story on the importance of this jet. Back in, I think it was 1999 and 2000, when Sonex was first flying their prototype airplane with a 6-cylinder Jabiru in it, they were using the Bing carb. Apply full power, climb out, no problem. Engine ran perfectly. Lower the nose, pick up speed, the engine would richen up and start belching black smoke, shaking, running rough. Sonex tried different jets, different everything, to no avail. And no one had told them about the carburetor bowl vent. And what was happening, they were drawing air from under the cowl there, and what was happening as they went up in altitude, the carburetor was trying to lean out, but at the same time they just had this bowl vent open to the inside of the cowl. And as they picked up speed and got to 160, 70 miles an hour, pressure in the cowl built up, hence pressure in the fuel bowl built up, pushed fuel through faster, richened the thing up, and caused them all the problems. That was one of the reasons they went to the AeroCarb on the Sonex. If they'd had this bowl vent hooked up correctly the first time, there might not be an AeroCarb today, who knows. But that's a very important part of it. This carburetor bowl vent, as we showed downstairs yesterday, needs to be hooked into the system on the clean side of the air filter. So in the Zenith installation, there's a little nipple on the airbox that you hook it to. An airplane like a Titan or a Kolb that doesn't use an airbox but just uses a tapered K&N filter, for instance, you run a little plastic line off the end of this and around to the end of that tapered filter, drill a little hole in it, stick that line in there, so it's on the clean side of the air filter. If you do that, then the pressure in the bowl is balanced with the pressure in the rest of the system. Want to sort of switch gears into how it works to control your mixture over varying altitudes. Okay, obviously you have a diaphragm here, and there's opposing pressures on either side of the diaphragm that will pull this thing up and down. Where does that come from? So we look in here. This is the intake end of the carburetor. This is the engine end. Up here near the top are these two inlets. See these two inlets right here? Okay. They come out right there on the bottom side of the diaphragm. So what are we feeding to the bottom side of that diaphragm?
Outside air.
Right. The ambient pressure of the outside air or the incoming air. I use the term ambient. That's probably not the right term to use, but I think it gets the point across. Whatever the pressure of your incoming airstream is gets fed to the bottom side of that carburetor. Okay, now, running up and down in the carburetor here is this piston, and somehow we need to get the other half of the equation, the engine vacuum, so to speak, to the top side of the diaphragm. Okay, when you look at this piston, here you see these two little holes. Those are on the engine side of the airflow. Airflow is coming in here like this. This piston creates the Venturi effect. You know, it closes down the passageway of the carburetor, so there's less pressure on this side of it, or vacuum on this side of it. Okay, that vacuum is fed through these holes just into the top of here or to the top side of the diaphragm. You see these two little holes here? Okay, then this is the engine side here, and they just go right through the piston and wind up on the top side of the diaphragm. So as you're flying along, you have this is the engine side, so you have an engine over here whose pistons are trying to suck air in. Okay, you have a butterfly here which controls ultimately the amount of air going in there. So the vacuum on the engine side of the butterfly is relatively, I don't want to say constant, but constant per RPM. Okay? But the vacuum on the upstream side of the butterfly is determined by what? By how far the butterfly is open. And this is one thing I want you to keep in mind here when we talk about prop loading. What happens in your airplane if you're flying straight and level and you pull the nose up? What happens to the engine? RPMs drop down. To get those RPMs back up, what do you have to do? Open the throttle more, open that butterfly more. So if you do that, what does that do in the carburetor? That exposes the top side of the diaphragm to more of the engine vacuum. Now, take the other case. You're flying along straight and level, put the nose down a little. Engine picks up in RPMs. Well, to bring the RPMs back to where they were, what do? You close the throttle a little bit. Therefore, you decrease the amount of engine vacuum that the top side of the diaphragm is seeing. Okay, so physically, mechanically, this is how all this works. So let's try and determine, first of all, let me try and draw a carburetor here. Okay, this is my biggest challenge, I gotta tell you. On top of the carburetor you have a dome, okay? And then you have a carburetor body and a outlet. Down here you got a fuel bowl, you got an inlet, going up to a diaphragm again. Okay, and your diaphragm goes right across here. Now, over here you have an engine, and over here you have outside air. Okay, let me lengthen that out a little bit, and inside, somewhere in here, you have a butterfly. Okay, now from this diaphragm is a tapered needle. Obviously I've exaggerated that taper, but to illustrate what I want to do, if your prop load and airframe drag is tuned to the size of the jets in the carburetor, then what happens, don't forget there's a needle jet right in there. Whoops, do it that way. And a main jet down in here that ultimately limits the factor. If your carburetor is tuned to your prop load and your airframe drag with the jets that are in there, what will happen is when you're at idle, the idle jet will be functioning. As you add a little power, it begins to put the needle jet, mid-range jet, into play. And the more power you add, the more this butterfly will open. Okay, the more the butterfly opens, here you have vacuum over here. Okay, so the more that butterfly opens, the more that vacuum from the engine is exposed to where? To the top of the diaphragm. Okay, the more vacuum at the top of the diaphragm, it will suck the diaphragm up into a dome shape, thereby pulling the tapered needle farther up out of the jet, giving more room between the needle and the side of the jet for fuel to go through it and supplying more fuel to the mixture. That's the whole principle behind it. Now let's talk about prop loading. Okay, if you have a prop that on static run-up will give you around 2,800 RPM, let's say 2,750 to 2,800, you will probably be tuned right about exactly to the way the carburetor comes set up from Jabiru. That's what Jabiru does with their airplanes, and that's what the engine is set up for, is one of their airplanes. So everything will be in tune. But now let's say you either have a very draggy airplane or you have a pretty coarse prop for a cruise prop. Now to get that same RPM, you have to open the throttle farther. Okay? Or in the case on the ground static, you won't get that 2750 to 2850 static. You may only get 2600, which means up in the air, to maintain a 2800 RPM cruise, you got to have that throttle open farther. So what does that do? That exposes the top of the diaphragm to more vacuum, pulls the needle up, and puts more fuel through there. But if you're still only turning, let's say 2800 RPM, because the needle is pulled up, you're letting more fuel through than what a Jabiru airplane would do the way it's tuned. So what do you have to do there?
Restrict the amount of fuel.
That's right, you have to reduce the amount of fuel flow. Two ways to do that, although there's actually only one way that's applicable to this. You can either make the needle fatter or the jet smaller, one or the other. Now, in the two-stroke world, there's a dozen different needle shapes, different tapers and so forth. You can switch needles. In the Bing 64 world, there's only one needle. So you need to change the jets. So when you take your Zenith 601 or 701 out to the runway and you apply full power and you see only 2650 RPM, you might expect that it'll run a little rich. Or if you take one out to the runway and power on climbing out, you're at 3000 RPM, you may find that it's running a little lean. Because the opposite will occur when you get up and set it for cruise flight. To achieve 2850 RPM, you don't have to have the throttle open nearly as far. So what does that do? That reduces vacuum to the top, lets the needle relax and go back in and shut the fuel down some so it will lean it out. Now, an example of that, our Lightning airplane. Okay, that's a real challenge because you want to have RPM for takeoff, but that's a slick airplane and prop on loads in a hurry. What we have to do with that one is lean that out a number of sizes. Otherwise it's going to run too rich. We will only achieve probably 2650 RPM on the takeoff roll with that thing because of the pitch that's in the prop. But up at altitude, full throttle straight and level will exceed 3300 with that same, just because there's not enough airframe drag to slow it down. So we have to tune the carburetor to the airplane. And you guys are doing Zenith 601s or 701. So what you have to do is go out and fly it. And you need to have an exhaust gas temperature gauge on there. We like to see at least one on each bank of cylinders, one on each side. A lot of guys now are putting on all six. Not a bad idea. It doesn't cost too much more with an EIS. Monitor all six. When you go up and fly, if your exhaust gas temperatures turn out to be around 1200 at full throttle climbing out, maybe 1250, and then after you level out and you pull that throttle back so you achieve about a 2850 RPM cruise, if you see your exhaust gas temperatures in the close vicinity of 1400, you've got it nailed. That's about right. And if you have it like that, then at 2800 RPM cruise, you're going to use 5 gallons an hour, maybe a little bit less. Okay? I get some calls from guys, not only Zenith, but others, who either they don't achieve that static RPM, so they got more prop load on it, and they call me up and they say, well, I'm using 7 gallons an hour. I have one Zenith guy who refuses to do anything but complain about it, is using 8 gallons an hour. But what he has is a Sensenit ground adjustable prop that he has cranked some pitch into because he wants speed. He's only getting 2500 RPM on a takeoff roll. He's got so much pitch in that prop, that's all he can get. So he gets up to altitude, full throttle, he can only get about 2850 RPM because he's got too much pitch in the prop. And what does that do? That full throttle exposes the full engine vacuum to the top of the diaphragm, pulls that needle up there, lets as much fuel flow through as possibly can go through, 8+ gallons an hour. You know, if you're not willing to experiment to get it to match your airplane, then you know, you're building the wrong kind of airplane. So as you go out and fly in the beginning, once you get those first flights behind you to get the feel of the airplane and all that, and get ready to start taking data, Push the throttle all the way in and take off roll and take careful note of what RPM you're seeing. Hopefully you'll be 2,800, give or take a little bit. Climb out to a good altitude, couple thousand feet off the ground, level out, and pull that throttle back to 2,800, 2,850 for a cruise RPM. Let temperature settle in, take a look at your EGTs and see where you're at. Hopefully you'll be right at 1,400 degrees, but again, it depends a little bit. If you've got maybe a little draggier 601 like Tony has with the big tires hanging out in the breeze, you may be a little rich. You may be a little rich. If you've got one